Welcome back, everyone, to the eCoreAcademy e-learning platform today. My name is AJay Raj, back with yet another geometry video for you all. Today's video topic is all about volume ratios, and we'll be moving into basically a further identification topic based off of our 3D concepts that we've been going off of for now constantly. We started with our one-dimensional concepts that are basically the building blocks and the fundamentals of our geometry Common Core curriculum. And then, of course, we built up into other enrichment topics in the one-dimensional and two-dimensional phases of this course, in which we looked at different relationships between figures and higher and more complex ratios. So now today we're going to be looking at ratios for three-dimensional figures. And we're going to be utilizing it for our volume. And we're going to show you the transition from 1D to 2D to 3D and how those ratios actually change all throughout this lesson shown here. But before we jump into the meat of today's lesson, please make sure to smash that subscribe button down below, hit that like button on this video, as well as turning on post notifications, and feel free to comment down below any feedback that you want us to implement in our later videos. We appreciate all of those things. As I was saying, today we're going to look at volume ratios, and we're going to discover we're going to answer this question, how can you develop ratios between figures and line segments? So what I'm going to be doing is I'm going to be moving between figures, line segments, and of course, our three-dimensional prisms, which fall under figures. And we're going to be showing you that transition all throughout. And this is going to cap off basically all of these relationships. And now we're going to be moving into basically more complex topics and a bit of a transition into Algebra 2. We're almost all the way there through this geometry course, so let's power through the rest. So let's start with similarity and scale factors. These are two terms that you should already be familiar with after following this Common Core curriculum, or if you follow your generic geometry curriculum. Let's look at similarity and scale factors, and let's see how we can actually implement them to our volume ratios. So let's look at utilizing similarity to develop our volume ratios, or ratios in general. So similar figures are two figures, or in this case, we'll say as two figures in geometry. These are bisecular comparisons. So similar figures are figures that have congruent corresponding angles and side lengths that are proportional as well. So that's identification for a pair of similar figures. And similar figures are also developed through scale factors. So their perimeters and areas will vary. This means that similar figures, you can have two similar figures, but that does not necessarily mean that similar figure pair will correlate, to another pair of similar figures. You're going to have different specified unique relationships that make each pair unique. And that, of course, is through scale factors. And you can also utilize scale factors not only to, compare your side lengths and develop it from there on, but you can also utilize it to calculate perimeters and areas when only knowing the value of one figure and the given ratio. So this is an example of two similar figures here. We know that they're going to be similar here because if I identify all of these corresponding angles as congruent, that means they must be similar. And that's not all, though. We have to also identify the fact that because they have all congruent angles, that means all the sides must be of proportionality. So if we look between these sides, F and L, well, let's look at the angles first. So angle F corresponds with angle H in the same location. They have the same angle measure as LI and OT do as well. So those are your corresponding angle pairs that are congruent. And of course, if we look at our side lengths, at side length FL, we have 15 here and 30 here at HI, corresponding sides. If we divide them, 30 over 15 equals 2. That means that is our scale factor. So it's SF, or scale factor. And with our scale factor, not only can we prove that we have similarity between two figures, such as these two triangles are shown here, but we can also provide external information that we might need to solve problems that come forth later on. That's also being said that if we know that we have one side that's similar, we know that these two triangles are already similar, we can utilize these given scale factors to calculate the missing sides. So say, for example, we know 20 here. That means we know that our scale factor is 2, so therefore this side has to be 40. Likewise, 25 and 50 divided by 2, that's going to be scale factor of 2. So they're all going to be of the same proportions and corresponding congruent angles. Now let's look at ratios of dimensions, part 1, and let's look at ratios and their effects on dimensions. So what we're going to be doing is we're going to be utilizing scale factors, what we know, and we're going to actually be using them to develop ratios. Now let's look at what the correlation between ratios and scale factors really are, and it's quite simple. A scale factor relates to similar figures. Now a scale factor is only identifying one type of dimension. A scale factor can only identify one-dimensional figures, and that's of course your lines. Can only identify length of lines, and that's a scale factor that's basically a reduced ratio of corresponding sides. And if you think about it, if you look at this reduced ratio, that's just saying that a scale factor is a specified type of a ratio. So that means a scale factor is a type of reduced ratio. So that means it's a type of ratio. And if the scale factor is a type of ratio, therefore we know that ratio can apply to all dimensions, as the scale factor only applies to one-dimensional figures. And when looking at dimensions, each type of dimension, we're only going to focus on 1D, 2D, and 3D throughout geometry. But of course, we can heighten those concepts later on in Algebra 2, pre-calculus, and so on and so forth. But looking at three dimensions, the common 1, 2, 3, we can see that each type of dimension is affected differently by a volume ratio or a relative scale factor, meaning that the scale factor is altered in some way in order to basically adjudicate to that specific dimension that you're looking for. And if we look at these two figures here, what we can do is, we can look at these two values here, and what we can do is, based off of these two figures here, we can utilize a scale factor in different manners, meaning that we can look at, 10 and 16. Those are side lengths of ours, so we can compare them, to this other square. We know that they're going to have common, angle measures, because all squares have 4 90-degree angles. All rectangles have 4 90-degree angles. And if we look at these side lengths, we can divide amongst each other. So 15 over 10 equals 1.5, as 24 over 24. Sorry about that. Bug just flew over my laptop. As 24 over 15 is also equivalent. 24 over 16 is also equivalent to 1.5, and therefore we can infer that these two are similar figures and that they have a proportion and scale factor of 1.5. That's how we calculate our scale factor as such when looking at two figures. Now, what I'm trying to show you is that looking at these two figures, we realize that they're two-dimensional, and you might be thinking, well, wait a minute, one-dimensional represents lines. Well, that's true, because we're only looking at the side lengths of each and every one of these rectangles, and each side length is only going to be a one-dimensional line segment. So now we have to try and transition into phases where we can look at a two-dimensional concept that is only specific to 2D objects, 2D figures, and that's area. And then when we look at three-dimensional objects, that's volume. And if you're looking at one dimensions of these figures, or if you're just looking at side lengths, it could be just a length, or it could be your perimeter. So those are the three values: perimeter, area, and volume correlate with 1D, 2D, and 3D. And so I'm gonna list those out and show you what equations actually prove and disprove each one. So let's ratios of dimensions part 2. Let's look at ratios and their effect of dimensions again, but now I'm going to try and identify these different dimensions and the different properties, such as perimeter, area, and volume. So the scale factor applies differently to the three dimensions, as each dimension will have different ratios. And these ratios are going to be in terms of the scale factor. So we're going to be using our scale factor, altering it to develop a new ratio that identifies and adjudicates to each and every dimension, three dimensions. So in terms of scale factor. So if we're looking at one-dimensional objects, it's going to be A to B. So that's basically saying that our scale factor is just going to be A to B. Now, all that is our scale factor here. So if you're thinking about it, it's basically a line. It's going to be a line segments here. So it's going to be such as 1 to 2. And this is going to be length / perimeter. And then here we have A squared to B squared. So now it's two-dimensional that we're looking here. So if you're trying to discover, the ratio between two different areas here, we would square our scale factor. So if we knew our scale factor, say for example, of a given side length of a figure, such as a square, we're going to square that given scale factor, and that's going to actually give us our area. So it's going to be a squared to b squared, and it's going to be, say for example, 1 squared to 2 squared, and that's going to be area. And of course, that simplifies to 1 to 4. And then 3-dimensional, it's going to be a cubed to b cubed, and that's going to represent our volume. So it's going to be 1 cubed to 2 cubed. These are just example numbers. If you got confused, I'm just utilizing example numbers to exemplify this, and that's going to be representative of our volume. And when you're looking at these separate values here, what I'm trying to get you to notice here is that if you're looking at a one-dimensional object, meaning that you have A to B here, that's going to be a line segment or a perimeter. So let's just utilize the line segment. So this is going to be 1D. I'll write this here, 1D. If we have 2 line segments, 2 lines here actually. One is 5 and one is 1. The ratio is just going to be the scale factor. We know our scale factor, you're just dividing the length. So 5 over 1 is going to be 5 to 1. And then for our 2D, say for example, we have 2 different squares here. We have rectangles here. So we have 1 rectangle here, 1 rectangle here. They have side lengths of 6, 3, and 3 and 1.5. Now we know that the scale factor is going to be consistent for all sides, same proportion for all sides. That goes for any type of similar figure. Remember, these are all similar figures. So we see here 6 and 3, that's going to be 2. So that means 3 divided by 1.5 must also be 2. And that means our ratio is going to be 2. However, if you want to know, if you just discover that, that means you're just doing a one-dimensional outlook here. That means you're just finding the ratio between the side lengths. Now we want to find the ratio between the area. So that's going to be 6 divided by 3 is 2. So it's going to be 2 squared. Going to be your scale factor squared, so it's going to be 2 squared 2. It's going to be 2 squared times your given area here, your given value here. So what you're basically doing here is you're going to take both one of your values given here that's specified. So it's going to be, say for example, 6. We're going to square 6, and that's going to be 36. And then we're going to square 3 here, its corresponding side length, and it's going to be 9. We're going to simplify this by dividing each side by 9 in this case, and it's going to be 4 to 1. And then if you look at that, it's going to be, original ratio was 2 to 1, but now it's just going to increase by 2 since you squared that 2, and you're going to get 4 this time. And now for our 3D, all you're doing is taking, say for example, let's take this given value here, and let's say that it has a similar, the same corresponding width here for a cube, to make a cube here. So we're looking at 3D, you're just going to square each one, cube each one, and I'll show you that in greater depth. B cubed, so you're just taking ratios. It's going to just be scale factor. Very, very simple. And this can also be put into fraction form, but if they specify that it's a ratio that they want in proper rational form, that means you would have to put A to B or in that form after you simplify your cubes or your squares, your exponents. Now let's look at one-dimensional ratios. So let's look at how scale factors affect ratios between perimeters. So when looking at an item that is one-dimensional or contrasting between perimeters of figures, so that's our one-dimensional concept. So when you're looking at one-dimensional between figures, you can either look at, separate side lengths, or you can look at perimeters, which is a sum of side lengths. And, you can always use your scale factors to discover your perimeters. So you can always utilize your scale factor as a ratio in order to describe the contrast between two different perimeters of similar figures. All you need to do is set up your ratios A to B in form of your scale factor, meaning it's going to be, A over B, and as A and B could be separate perimeters or side lengths. So those are your 2 given figures here. So what if we have, these triangles given here, and let's say that they're equilateral triangles. That means they have all equivalent angles as shown. So that means they're similar. Now what we're going to do is we're going to assign a given side length here. So that means, say for example, we're going to put 3 and 18 here. Now we want to discover these, the ratio between the perimeters of these 2 objects. So we want to describe let's name this as A and B, and we were trying to find the perimeter So we're going to try and find this perimeter ratio, the ratio of perimeters. What we're going to do is we're going to take our scale factor by taking one corresponding side divided by the other corresponding side. 18 divided by 3 equals 6. And since we're given 6 here, well, all we need to do is, leave it as 6. And we're going to multiply, or sorry, no. We're gonna describe this as 6 here, right? But in essence, all you really need to do is take this fractional form and put it back into your rational form, meaning 18 to 3. And all you're going to do is divide each side by, the maximum account that you can put it at. So since it's 6 here, that means that triangle B is going to be 6 times the value of triangle A. So that's the same as saying 6 to 1. But since we're putting this in terms of A to B, it's going to be 1 to 6. So always keep that constant. If they don't specify which one to put first, just realize that it's going to be in alphabetical order and that it was stated for a reason. So stay safe in that aspect. Now let's look at two-dimensional ratios. So let's look at how scale factors affect ratios of areas. So when looking at an item that is two-dimensional, or comparing the areas of two-dimensional figures, so when you're trying to compare the areas of two different figures, you square the scale factor and utilize its inverse. So I'll show you how that's used. Like I was doing in this problem here, what I mean by inverse is if you know basically 1 to 6, if you know your ratio here, all you need to do is square root each side by 1. So if you square root by 1, you're not going to get a value that's different. So you don't have to work backwards in order to find your ratio, the relationship between your scale factor and ratio. If you're given your scale factor, if you're given your ratio and you want to discover your scale factor, the ratio is the scale factor as represented. And one thing that I really want to address for all problems is that, say for example, you aren't given these side lengths. So if these side lengths were not known here, what you would do is, well, if we weren't given these side lengths and we were also given the ratio, what we would do is we'd work backwards. Meaning, if we're given this 1 to 6 ratio, we know it has to be from A to B. So, we know that, 1 to 6, there's nothing that we need to do because you didn't square or cube anything. That means the ratio is going to be 1 over 6. So what you can do is you can describe the values. If you're given, say for example, one value here and only one value on this triangle here, on triangle A, it's 1/6 of the value of B. Oh, so I'm going to multiply 6 times 3 and get 18. So you can always work backwards as well with these ratios. And it's mainly what it's going to be used for later on when it comes to more challenging problems. So let's look at how scale factors affect ratios of areas. As I said, you can utilize the inverse, and you're going to you're going to square the scale factor in order to discover the relationship between areas. When discovering the ratio between two areas of two figures, once you're given the scale factor, all you're going to do is, like I said, you're going to square each given corresponding side length, and you're going to square them together in order to get your ratio between areas. Now, when discovering the scale factor, what you're going to do here is, since we're trying to discover the ratio, what we're doing is we're using our scale factor, and then we're going to alter it to discover a ratio. Now we're going to work backwards. We're going to utilize a ratio, alter it to get back to our number one scale factor. So remember, you're squaring basically your scale factor here. What you're doing is you're squaring your scale factor. And when you're squaring your scale factor, in order to get back to that, you're going to square root the volume ratio here. Your area ratio. So it's going to be square root of A squared to square root of B squared. And that actually cancels out, but in this form, it's just going to be A and B, or square root of A and to square root of B, because you've already altered A and B by squaring them. So that's in the form of just ratio A to B. That's what you're going to do here, square rooting it. But in terms of this equation, this is what you would do. So very simple. Now let's look back at these triangles. Let's plug in different values this time. So let's use 5 and 15. Use 25 actually. That's what I have written down. So 5 and 25. With these given values, 5 and 25, what we're going to do is we're going to try and develop, our area ratios between these two triangles. We're going to assume that they're also equal angular, meaning that they're equilateral as well. So they're similar, and they have all equivalent sides within each other. We're going to discover what our area ratios are, and then we're going to try and work backwards and also represent how, if we're only given one side length and, our area ratio, how we can discover the next side length, corresponding side length of the other triangle, and all of the side lengths of the other corresponding sides. So what we can do here is we can take our values here. So we have 25 and 5, so we'll put 5 to 25. And then we know 5 squared is 25. We can square our 25 here, though. So 25 times 25. 5, 2, 10, 2, 0, 0, 1, 4, 5. And that's going to be 6, 2, 5. So that's our value there. It's going to be 6, 2, 5. Now what we're going to do is we're going to divide each side by 25, and we're just going to be simplifying that. So we know 4 into 100, and then 6 times that. So we have 6 times 4, which is 24, plus 25. So our value is going to be 25 to 1. That's going to be our volume ratio, our area ratio. And then, if you want to discover your scale factor, just square root each side, 25, and square root of 1, we get 5 to 1. As you can see here, that's a ratio between 5 and 25. It's 5 to 1. Between 25 and 5, that's 5 to 1. And you can also utilize this by, say, for example, we didn't know 25 was here. We only had 5 here, and we're trying to find this corresponding side length and find all the sides of this corresponding triangle, which is not always the case, but just in this scenario, what you can do is you can multiply this 5, by your given 5 here from your scale factor. But if you want to discover the area here, all you would do is plug in, this value here of 25 multiplied by 25, and this is going to be 625. That's going to be our area here, and then our area here is going to be, our area is going to be 625 times this given area here. So it's going to be 625 times this area. I'm sorry, 25 times. I apologize. 25 times this given area here, but that's simplification from 25 to 625. And now let's look at three-dimensional ratios. How scale factors affect ratios of volumes. When looking at an item that is three-dimensional, or when comparing the volumes of two three-dimensional figures, you can cube the scale factor and utilize its inverse. So same exact thing that we're doing with area ratios and like I said, two-dimensional ratios. We're gonna look at 3D ratios, and 3D ratio property is of course your volume. That's the only new concept that you're gonna come across is your volume. That's what creates 3D objects. And you can use a scale factor and utilize its inverse as well. So when discovering the ratio, all you would do is cube the scale factors this time. Cube the side lengths this time. And that's in relationship to your scale factor. You just cube your scale factor in this case. When discovering the scale factor, moving from ratio to scale factor, you do square root of a cubed to square root of b cubed. Or you could just do a square root of a to square root of b in terms of a to b, after simplifying this equation here. Now let's look at our final example here. We have a cube here, and it has a 4 centimeter. We have 4 centimeters here, and let's assume that we're given another cube. So cube number 2. So this is cube 2. You're going to come across a lot of problems here that actually only show one cube, but don't actually describe another one. And that's the type of problem that I've come across multiple times, and thought it would be interesting to actually go through that. And cube 1, let's say that cube 1 actually has a length of 2 centimeters. So it's going to be 4 centimeters here for cube 2 and 2 centimeters here for cube 1. Now what we're going to do is we're going to discover our volume ratio. Like I said, this is the whole topic that we're building up to today, so pay close attention. Very simple, though, when looking at building up off of our area ratios. So what we're going to do is we're going to look at our ratio here. We're going to say a cubed to b cubed. So let's name cube 2 as b. Actually, let's name it as a, because we want to move from large to small. So let's name this as a and name this as b. And this is our imaginary cube 1. So it's a and b. So we're going to move from a to b. So we know that a is going to be 4 centimeters for its side length. So 4 to 2. That's our ratio here. That's our one-dimensional ratio. Now we're going to cube each side. So we know that 4 cubed is 64, and 8 cubed is 8. And then we're going to divide each side, simplify it out, and we get that 64 divided by 8 is 8 to 1. So that's the ratio of the volumes, meaning that cube 2 or cube A is going to be 8 times the volume of cube 1. We can move backwards, by doing, say, for example, we want to discover what the actual ratio was, what the actual two numbers are being compared to, what they actually were. And in that case, we can cube root each side. So 64 to 8 is shown here. It's our unsimplified ratio. And we're going to cube root each side. And we get 4 to 2. Moving backwards, just as I said, the original ratio here correlates. And finally, if you were only given, say for example, if we were only given our value of 2 centimeters and we didn't know it was 4 centimeter length, but we knew that cube A existed, and we were given that volume ratio of 64 to 8 or 8 to 1, we wanted to discover what the side length here was. All we would do is find the corresponding side length here, so 2, and then what we would do is cube root each side of our given ratio here. Like I said, 64 to 8, and we can multiply it to find this missing length here. And also, if you did not know the value of this volume here, and you knew the volume of cube 2, and you wanted to discover the volume of cube A, all you would need to do is multiply the volume of cube 2 by your volume ratio. Same thing with your area ratio. If you wanted to discover the areas of these two, if you found the area of this triangle here, all you need to do is multiply it by the scale or volume area ratio to discover the larger triangle. Vice versa, you can divide it from larger to smaller. And finally, I just want you guys to remember the following, that ratios can only be used for similar figures. So this only applies to similar figures, not figures that are out of this category. It just does not apply because they do not have corresponding side lengths or corresponding angles. And also, you can use your ratios and multiply them to given dimensions, meaning you can multiply them to given dimensions such as your area or your volume or side length and length to calculate a missing figure, meaning like I showed you the volume. If you found the volume of one figure, you can use, and you didn't know the volume of your second figure, you can use your volume ratio in order to multiply it to that given original volume to discover the missing volume. Once again, everyone, that has been the eCoreAcademy e-learning platform today. I hope you all enjoyed. Please make sure to like and subscribe and hit that post notification bell to get notified on any of our channel's latest uploads, so you don't miss out. And feel free to leave a comment down below. We really appreciate all of your constructive feedback. We'll try and implement it every single video that we go along. Because of course we're catering to you guys, and what we offer as an eCoreAcademy e-learning platform is all at our website at www.eCoreAcademy. It's full unlocked access to what we actually offer as our own e-learning platform. We have full unlocked access to integrated quizzes, note sheets, and worksheets that go along with each and every single video, organized into their own separate lessons under their own courses and subjects. We have other tips and perks and perks and tricks that are added, to standardized testing, all that stuff, all that sweet stuff, and progress checks that go along with everything else. We also have our contact information there, and all you need to do is make an account for free there, and you get full unlocked access to everything that we have there. So please make sure to sign up and visit and see what we have there. We took a lot of time to work on that. Also visit also email us at eCoreAcademy@gmail.com if you have any questions. If you just want to reach out, some offers that you have, or if you just have some questions on any of your lessons, we're more than happy to respond. And finally, visit all of our socials in the description box below. We have the full links down there at Facebook, Twitter, and Instagram. See what kind of content we have there aside from our YouTube channel on our website, and use those mediums to share all of our videos. Once again, everyone, I hope you guys enjoyed. This has been AJ, and I will see you guys in the next one. Peace.